Hello, everyone. Welcome. Thanks for joining me today on our diagnostic training session. Sorry, we're a little bit late today. We got caught up in another room with some training. So if you have any questions and you're watching along on Zoom, if you look at the top or the bottom of your screen, wherever your Zoom controls are, just click on the Q&A button. Click on that, type in your question, hit submit, and I'll get to those questions at the end of the session. If you're joining me live on YouTube, just feel free to use that live chat function on YouTube as well, and we'll be able to get to those questions once again at the end of the session. So my name is Jason Gabrinas. I'm one of Snap-on's National Diagnostic Technical Trainers. Been in the training department the last 8 years, traveling around North America, helping techs and shop owners get the most out of their diagnostic equipment. Before I did that, it was a couple of years as a diagnostic sales rep with Snap-on. So I had 30 different Snap-on franchisees I worked with, as well as the shops that they serviced in order to help everyone get the most out of their diagnostic needs. Then before that, it was 8 years at Subaru. So I was a factory-trained Subaru technician. And I guess over time became that diagnostic guy in the shop, right? The drivability guy. You know, I always had the drivability problems, the intermittent problems, the weird wiring problems would always seem to show up in my bay. And that's really where I cut my diagnostic teeth, was trying to figure out all those weird problems that would show up. Then before that, a bunch of other miscellaneous wrenching jobs. Been over 25 years under hood experience for me. So today we are talking about component testing. We're continuing on our component testing series we've been doing for the last few weeks. And today focuses on the ignition coil. So the ignition coil works on what we call the principle of mutual induction. So what mutual induction is the transfer of energy from one coil to another coil when they're placed in close proximity to each other. Now there's going to be one coil connected to the voltage source, so that I'd call that the input, and that is the primary winding of the coil, or we call that the primary side of the coil. And then another coil is connected to the another circuit, the output side, I would say, and that is the secondary winding. So we look at this diagram of a coil down here. We have a common, usually it's a piece of iron in there. It's a common conductor in there. And then around that, we have turns of generally copper wire. In this case, in this diagram, we have 10 turns of copper wire on this side, on the primary side. And we have 1,000 turns of copper wire on this side, on the secondary side. So the difference between these two, 10 to 1,000, that's 100 times difference, right? 10 times 100 gives us 1,000. So that is 100 to 1 difference between each side. So if I apply voltage over here, and when I apply a voltage to a coil around a conductor, I get a magnetic field. So on this primary side, I am putting in 14 volts, 14 amps. That gives me 196 watts of energy to transfer. It's going to generate that magnetic field. Once we start generating the field, it's going to grow and expand, and then eventually we will remove that voltage going in there. When we do that, the magnetic field will collapse. When it collapses, it transfers that energy it has stored over to the other side, that secondary side. So due to the difference in the amount of wire we have, that steps up the voltage going across. So in this case, it'll be by a factor of 100. Now the 196 watts doesn't change. That's going to go across. But now we have 1,400 volts. And then the amperage actually goes down by a factor of 100. So we have 1,4 hundredths of an amp. So this principle, this mutual induction principle, is how we get 20, 30, 40,000 volts out of a coil, depending on how it's constructed and how it works, right? So that is our mutual induction, and that's how it works. So we have a little animation of how it works. Super simple little animation here. We flip the switch, we start the voltage and current flowing into the coil. That is what we call dwell, and that is where our primary side charges and generates a magnetic field. We remove the electricity, it collapses the magnetic field, transfers over to that secondary coil, and that gives us the juice to enable us to jump that gap on the spark plug and explode our air fuel mixture. So that's really where it comes from. This is a pretty standard secondary ignition pattern. So this would be what my coil is putting out. All right, so this is the after effect of after my coil is fired. So first we see that dwell section, right? That's where that primary coil is charging, starting to generate its magnetic field. As more energy goes into the coil, the magnetic field grows and has more energy with it. Usually you'll see some oscillations at the beginning where it's just kind of starting to fill up that coil a little bit. Then it'll level off. And then when it's time to fire, in order to jump that spark plug gap, we're talking about creating a path, as the way I like to, a good analogy for that, creating a path from my ground electrode to my my center electrode there. And in order to do that, in order to make that path, to cut that path through the molecules in there, we need a lot of energy. So we need a lot of voltage, and that's why we have this very high voltage spike here, and that they call that the firing line. So that is the voltage to cross the spark plug gap. Once I've made that path, then cross the spark plug gap, super easy to keep that, or relatively easy, I shouldn't say super easy, but relatively easy to keep that spark going. So the voltage requirement drops considerably down here. And this is what we call a spark line. This is the spark actually occurring. So after that first jump across the gap, then it just maintains. And that is where my burn is. This is our burn time right here to here. Depending on the efficiency of the coil, you may see these oscillations down the other end. If it's not very efficient, it's going to have a lot of extra energy left over, and it needs to dissipate before the next time it charges. And that's why we see these, they call these coil oscillations here. That is the coil relieving itself of the excess energy that's in there. You may have also heard the term wringing out the coil. So it's kind of wringing back and forth in there. If you think about like wringing out a towel to get out the extra water, we're wringing out the coil to get out the extra energy. Then it'll level off, and then we have dwell start again and brings us back over here to the left-hand side. So that is a fairly standard output pattern of a coil. Now, we do have other classes where we talk about how we're going to interpret this, and we're not really focusing on that for this course, but there are other courses. I would encourage you to go check those out, a couple other ignition training classes where we talk about the differences in firing line height and what a spark line means when it goes up at the end versus where it goes down at the end. We talk about all that in those other classes. So I definitely encourage you to check those out. We're just focused on how are we going to test this coil. All right. So using this though, having this mutual induction between the primary and secondary side allows us ease of testing. So I'm going to test whichever side of that coil makes it easier for me to test. Now, the most detail I will get is going to be out of the secondary side. So that is this top pattern right here on this screen I'm showing you. So we have dwell right there. We have the little squiggly lines, goes through, and then we have our voltage spike jumps up right here. So that is my secondary voltage right there, jumps right up. And then for the firing line. And then we have my spark line over here. And then we see the coil oscillations at the end. Now, this is the primary side down here that we have hooked up. And we see, once again, oscillations for dwell, goes in, firing line, spark line, oscillations at the end. And you do see quite a bit more detail on that firing, in that secondary signal, because the voltage differences are going to be much greater because of that step up factor. Right? If it's 100 to 1, 1,000 to 1, 10,000 to 1 difference, that's going to be your difference in voltage too. Right? So if I have 14 volts here and I have 14,000 volts here, possibly, depending on what it is. So the ups and downs are going to be more pronounced. But if I can't get to this coil, give you an example, Ford Edge we were working on one day as a transverse mounted 6-cylinder. If I wanted to do secondary testing on those front 3 coils, super easy. They're right there, real easy to get to. The 3 coils in the back, not so much. It's underneath the bit of the firewall and the cowl. And then, of course, we have the intake plenums on top. This is really hard to get get a probe back there. So in that instance, I might use primary testing in order to still see what the signal is and what the coil is producing. All right. So what kind of tests can we do on an ignition coil? There's a few different ways to go about it. Many of them are voltage, and then one of them is amperage. So if we talk about ignition control signal, so if I think I have a faulty coil, it could be the coil, or it could be what's controlling the coil, right? So in many cases, it's the ECM, or there could be a dedicated ignition control module. But in this case, I'm just going to use a simple back probe at a coil. This would be on a coil unplugged vehicle, but any vehicle with a coil will still have a control signal. It just might be a little bit different. But on this vehicle, it's coil unplugged, and we would simply back probe at the control signal, which goes back to the PCM on this vehicle as well. And then in most cases, many cases anyways, you will see a 5-volt square wave. It's on, it's off. And in this case, on this vehicle, when it's on, that is telling the coil it is dwell time. It's time to start charging up that primary coil. And this is where we should be in dwells when we see 5 volts. When the 5 volt goes away, that's when it's time to fire. So if I were to overlay the two, use 2 channels on my scope, and I would see the control signal as well as the secondary signal, you can see how they match. So I have my control signal here. Here's where dwell needs to start. And lo and behold, dwell starts on my secondary. And then it holds and holds and holds, and that's where it's charging. And then when it's time to fire, 5 volts goes away, and then you see my firing line happens right then as soon as that 5 volts goes away. All right, so that's how, in this case, PCM controls it. It's going to be fairly similar across the board, depending on what kind of vehicle it is and how it's set up. It's going to be fairly similar signal that we would get there. Next one's going to be primary voltage. So I want to make sure there's voltage going in, and I can also see how the coil's operating. I can see that firing line in this case. So in this case, we're going to look at the voltage supply line. Back probe there as well. Don't need anything fancy, just back probe on the coil where the power goes in. In this case, I see primary voltage on this vehicle. Now, in this case, the way the coil is set up, I don't get as much detail as I would on some other vehicles with the primary side, but I still can't see what's going on. So alternator voltage, the vehicle is running, of course. So we have 14.4 or so. And then this dip, where it starts to dip, we can see that's where dwell starts. As dwell is starting, the voltage is coming out and it's going into the coil. So it's being relieved from the wire, going into the coil. So we have this little drop right there as dwell continues. Once dwell is done and it's time to fire that spark plug, we have that big jump. Goes up to 18 volts on this side. And then it comes back down where the spark line would be. Now, as I said, not a lot of detail there. Just kind of goes right back to alternator voltage in that case. But I can at least see the firing line on this particular vehicle. If I were to line that up with my secondary, we can see there's my dwell. There's my dwell, starts to dip. There's my firing line. There's my firing line right there. So we'd be able to detect the voltage in there. Now, so far, we've done 2 tests on voltage, and we haven't needed anything fancy. This one, not all that fancy, but we do need an accessory. So if we wanted to check the secondary voltage on a vehicle, I think you'd agree vast majority of cars nowadays are coil on plug vehicles. We don't really talk about cars with plug wires on them anymore because they're few and far between. I mean, I guess on Chevy Vortec trucks, there's quite a few of them, but I could still test the coil on those vehicles as well because there's individual coils on each individual cylinder. In order to check coil on plug vehicles, you would need some sort of an adapter. Now, we have a couple different ways to go about it. Easiest way, in my opinion, is to use the flag pickup. You can just set it right on the coil or to the side of the coil and be able to pick up the signal, right? The secondary signal. Also, I'd like to note, when it comes to secondary testing, you do want to check a wiring diagram and see how is that vehicle set up. There are some vehicles where you cannot get a secondary ignition pattern on there because of how the coil is designed. Many of these vehicles with that design, you absolutely can't, but you'll see that it's integrated ignition control module with it. I know a lot of Nissans are like that, and I know like the Hemi engines on Chrysler vehicles are like that as well, where you can't get a secondary signal off it. So you need to use primary or current ramp, which we're going to talk about in a minute. But here's my secondary test on this vehicle. I can. So it's next to the coil, and then I see, well, there's dwell, there's my firing line, there's my spark line, and I can see what's going on with the coil, make sure the coil is firing. If I was going to check this, I want to check all the coils and make sure they're fairly even at the same RPM. I want to make sure the firing line's the same and make sure that it is even firing. Right, so we'd be able to see that there. If it was a weak coil, you really wouldn't have much of a firing line there, and then you definitely wouldn't get a spark line if it's too weak. It might not be firing at all. You'd be able to see that as well. So that is a secondary voltage test. And as I said, we go way more in depth on secondary and interpretation on that in some of our other classes as well, which are available on YouTube. So definitely check those out. And then we have a primary current test. So this is using a low amp probe, and this is a very handy test, and we can see what this coil is doing. So there'd be a low amps probe connected to the coil feed circuit, just like we had tested earlier on the primary. We can test this with the low amps probe as well on the coil feed circuit. So just clip it around the wire, and we should see something similar to this. On this particular vehicle, we see how the coil ramps up, the current ramps up. We do want to see a nice smooth ramp like this. If it went up very sharply, like almost at a 90-degree angle, that would indicate open or short inside the coil, and that is a bad thing. So we wouldn't want that. I'll actually show you. I have a good example of that in a few minutes. So if it goes up sharply and then over, that's a problem with the coil. So we want to see it go up nice and smoothly like this. In the case of this vehicle, this manufacturer decided they want it to be a current limited design. So that means when it gets up to a certain amount of current, it just kind of levels off right there. So we see that rounded top, and it looks like it's around about 12 amps is where that stops. So it just rounds off and it levels off until it fires. When it's time to fire, voltage goes away, so the amperage goes along with it. So we see a rapid descent to 0, and then it goes over like that. And then the next time it fires, same thing, right? So it'll be multiple. Every time it fires, it'll look like that. We wanted to see how that compares to my secondary. See the current ramp there. We see the dwell there, and we see how the current relates to dwell and the charging of the coil, right? As we build up the charge in the coil, the amperage increases going in there as well. So we should be able to see that relationship if we look at both on the same screen. All right, so let's talk about a real world case study where we might be able to see this and put this to use. So this is an 06 BMW 330xi, complaint of a misfire. Rough running, engine light on, all that good stuff that happens. So we pull it up on the scan tool. First thing we want to do in any diagnostic workflow, if we have an engine light, if we don't have an engine light, if we have a drivability problem, really no matter what, we want to go through and we want to scan that vehicle, scan the whole vehicle, check all the modules, make sure we don't have a pesky code in some other module that doesn't have a light, right? We want to make sure that we're scanning the whole vehicle. So on Snap-on Scan Tool, on most newer cars, 06 and newer, you're going to have this code scan function, right? So we go up on the top, click code scan, and then it asks us, do we want to do a pre-scan or a post-scan on the vehicle? Of course, we want to do a pre-scan. I haven't done anything else to it, so I want to see where am I at? This gives me my baseline. How many codes do I have? How messed up is this car, basically? So we'll do a pre-scan, saves it, goes through all the different modules. You'll notice it found 52 modules on this vehicle and comes back with one code in the engine. So I have a 29CF code. So what's a 29CF? If you're not familiar with many European vehicles, will give us what we call a hexadecimal code. So this is a BMW hex code. It's what they call it. So 29CF, and that translates to a combustion misfire on cylinder 3. So on regular OBD2 codes, peak codes, that'd be a P0303, right? So combustion misfire on cylinder 3. Since this is on a Zeus, I have Intelligent Diagnostics at my fingertips, so I can just simply click on where it says diagnose here on the right, and it's going to bring me into my Intelligent Diagnostics screen. Now, if you're not familiar with what Intelligent Diagnostics does for us, we will see that it gives us a nice layout of what's going on with the vehicle. It gives us our list of codes on the top, and then it gives us a repeatable diagnostic workflow to work off of. It takes all the information on the tool for that vehicle and filters it down just to that specific code, to that specific vehicle. All right, so we have our 29CF. First thing we want to look at on any vehicle and any workflow is you're going to want to check TSBs, right? So TSBs, in this case, I have 3 TSBs available for this code for this vehicle. So if I click on that TSB card, it's going to come up. It's going to give me my misfire due to a failed ignition coil is the first one. The other 2 are spark plug application charts. So I think in this case, unless we find a problem with the wrong spark plug in there, first one I want to look at is the first one. Engine misfire due to failed ignition. All right, so it gives me my TSB information here, bulletin published, go down a little bit, little ways, and according to this, says the current ISTA misfire test plan. So ISTA, that's the BMW tool. The test plan for these engines can be lengthy to complete and does not provide an effective method to diagnose a faulty secondary ignition component. So in this case, well, yeah, so I guess the factory tool doesn't give you as much information as they'd like you to. So we go through and we diagnose. The easiest way to diagnose this is, does it have a Bosch coil? If it has a Bosch coil in there, they're instructing you to replace it with a Delphi coil. That's pretty straightforward, right? If I see a Bosch coil, I guess they must have had a lot of problems with them. So we need to replace that. It says if the coil was replaced previously with a Delphi part, you do not need to replace it. You need to look elsewhere, apparently. Coil could still fail, I'm sure, but it does seem like there's a high failure rate on those Bosch coils that originally came in the car. So if you see a Bosch coil, you replace it with a Delphi coil, and magically it gets fixed. So that might be a good place to go. Let's get a little bit more information, though. Back to my Intelligent Diagnostics Fast Track Intelligent Diagnostics screen. We did the TSBs. Now we'll look at real-world repair information. So this is based on over 1.3 billion repair orders. What was repaired for this problem? So we see that this mileage base goes up to 200,000 miles. And then based on each mileage breakdown here, what was done most commonly. So he's overwhelmingly overall 847 times over this 200,000 mile span, replace the ignition coil. Seems to peak around 100,000 miles with 270 instances at that mileage. So you can see just looking at this, looks like it might be pointing us to the coil. Number 2 is the spark plug. If I replace a coil while I'm in there, probably going to replace the spark plug. So that makes sense, right? That would happen. But it does see overwhelmingly that looks like a lot of coil things getting pointed in the right direction. I go a little bit further down. Let's go next to check data, smart data. Smart data is going to take all the PIDs available for the vehicle, filter it down to what PIDs do I need to diagnose this problem. And then what else it'll do is it'll set these flags, right? So it has these blue outline flags and the red flags. The blue outline flag means that parameter is being monitored for known good and bad values. If it goes outside of that, whatever the range is set, it will turn red and will direct us to, hey, we need to take a look at this. So we see on cylinder 3, they call these true running values on the BMW. So that's like their misfire count. All right. So you see true running value is negative 1100. That's pretty negative. It's not contributing to the engine. So we see that, and that indicates, well, we have a problem on cylinder 3. If we go down a little bit further, functional tests and resets, probably not really applicable to this case as a coil. There's not usually many functional tests, maybe turn off an injector, something like that. But if I think I got a coil problem, let's go test the coil. So next step is guided component test meter right here. I go into guided component test meter, it'll filter out what tests I could do that would pertain to a cylinder 3 misfire. So in this case, a compression test using voltage, ECM information, and ignition tests. So talking about coils, let's look at the ignition tests. Go to the ignition tests. I could go to component information to see how the ignition system operates. We already kind of went over that. So we're going to go in and check some primary tests. We also do have secondary tests in there, but we'll go to primary tests. Now, the thing about guided component tests, I should back up a little bit. If you're not aware of what guided component test does for us, there's over 5 million guided component tests inside the tool at any given time. Goes all the way back to 1981, covers a whole slew of vehicles, and it covers many systems and components on the vehicle. So this filters it down in Intelligent Diagnostics to what pertains to it. So in this case, ignition system. I have a few tests that I can do here. The one I want to look at is the current ramp test. See how that's operating. So it's going to tell us use a low amps probe and then hook it up to the tool, channel 1 and ground. We scroll down a little bit. It says put it around the feed wire, as we had said earlier in the presentation. Put it around the positive wire there. In this case, we're using the wireless scope option for this. Wireless in that case. And then you see it gives us a known good pattern here. So here's what the coil ramp, current ramp should look like on a normally running vehicle. Now, if I look down a little bit lower, it also says if it has multiple coils, which it does, current flow through each coil should be about the same. And if it is multi-strike, which this vehicle is, it may have multiple strikes at low speeds or during warm-up. So it's trying to use as much energy out of that coil as possible to burn as much fuel as possible to make sure we have complete combustion in the cylinder. Usually at low speeds, like something like that. This BMW uses it. There's Fords that uses it. I'm sure there's other manufacturers that use that method as well. So we have right here the current ramp, the initial ramp, and then each additional spark going on there. So if we hit view meter, it's going to open up. It is going to set the range where I need to go, the vertical range. So we call that the scale. And then it also sets the sweep time where I need to be. So if I have this low amp probe hooked up correctly, I should see a pattern on the screen. It makes it very, very easy to use. I don't need to remember settings. I don't need to know how to set it up. I just follow the instructions and look what's on the screen. All right, so in this case, I see pretty sharp rise there. I'm going to go up and make this a little bit bigger. So if I have my meter button right there, it's going to open it up, just makes it a little bigger, gets rid of that known good pattern. I know it didn't look like that known good pattern anyways. So now we see that sharp inrush of current right there. That indicates open or short inside the coil windings. And then we see the current ramp resumes over here. Subsequent strikes, we also have this excess vertical. And then we also see an interesting trend here as well. It's increasing amperage every time that it fires there as well. So that's a little odd where it kind of ramps up like that. So in this case, that's a bad coil. We have some sort of problem in the winding there. Don't really know what it is because I'm not going to take it apart, but I know that's not right. So we need to fix it. So we replace it. And there's the good pattern afterwards. We want to always verify our repair after the fact. So there's our known good pattern here. So we can see that it goes up and comes down. And then we see our subsequent spikes are fairly level. They're lower than the initial spike. And they may even be going on a slightly downward trend. That's a little bit more the way it should look. Now, why do I have these sharp ramps on my subsequent spikes? So because it's got to fight the energy that's already in there to charge it back up. So it just has to charge it back up that little bit every time it needs to fire. So we do have a little bit to overcome there. So we have that higher amperage requirement for that. So that's a known good. Once again, that's the known bad. So we can see the amperage requirement was considerably higher there as well. So it brings it down below 10 amps, around about 9 amps instead of 12 amps. So we can see less amperage required, pattern looks better. Once we do that, we clear it, we scan it, we check it for codes, make sure there aren't any. In this case, there weren't any. 52 systems, all clear, all green circles, looks good. Cool. So that is our academic material, we'll say. Now let's go live on a car. So I see some comments coming through on YouTube. Thanks everybody for saying hi. I see we've got people from a couple different places. We got Edgardo from Cali, Colombia. Thanks for checking in on there. And Algeria. Oh, cool. And let's see, where else? UK. Cool. So let's see everybody ready to learn on YouTube. Thank you for that. If you have any questions on YouTube, by the way, if you're joining us late, just use that live chat and I'll get to the questions at the end. Also, if you're joining us on Zoom, make sure you use that Q&A button in there as well. And also Joseph, he says, why do I always use a BMW for case studies? It just happens to be the ones we have some material on. We have a couple BMW guys help us out with that. But in this case, in this live study, I'm actually using a Toyota. So it's not always a BMW. Oh, yeah. And the other reason, too, is we have this BMW demonstration board, too. So that works out pretty well. We can simulate patterns off of BMW. That's another reason we do that, too. Sometimes we try to mix it up. I'll tell you, be honest with you, a lot of people have told me, why do you always do it on Subarus, too? Well, it's because I'm a former Subaru tech, and that's where a lot of my knowledge base is there as well. Hey, Calgary as well, Mr. I Am No Sleep. So anyways, let's go live on the tool and do a little bit of investigation as to what we can do as well. So I have a vehicle loaded here. It is a 2016 Toyota Camry. I want to do a code scan. I want to see what's going on. It's got an engine light. Do that pre-scan. It's going to scan through that vehicle for me. Demo vehicle takes a second. And I get a code. P0356, ignition coil F, primary, secondary circuit. So we have a problem with a coil F. If I hit diagnose, you're going to see my information here, ignition coil F. No TSBs to worry about. So think about the time savings here. This just dawned on me today. So we're talking about some with some new sales reps today. We're training them. And this popped into my head today was, well, if I see that I don't have any TSBs that relate to that, I don't even have to think about searching through a couple hundred TSBs to see if I have one, right? It already told me I don't. So the no TSBs apply in this case. So that's a huge time saver. I don't even have to think about TSBs because I don't have it. Nothing applies to that. Next one, we go over to our top repairs graph and we see, yep, ignition coil number 1, spark plug number 2 makes sense. Ignition coil connector, that's a little curious. That's a pretty high number there. So maybe they had some problems with the wiring harness on that. right? So I'm thinking though, as it says, ignition coil F, primary circuit. So A, B, C, D, E, F, that's number 6, right? Coil number 6. Smart data, I could see, maybe I'll see some misfire data there. Functional tests and resets, maybe I'll be able to turn a injector on or off, something like that. But in this case, I'm going to check my guided component tester. All right, so we see relative to a misfire problem, coil problem, could be crank or cam sensor related as well. Ignition control module, I'm just going to go to ignition tests. Now, before I do go to ignition test, though, I'm going to back up one step. I'm going to come down here and go to the bottom because I want a little bit more information about this vehicle. I'm going to check the wiring diagram for this problem. Wally, I am using a Zeus, by the way. So down here, we have repair information. So if you have a subscription to Shopkeep or Mitchell over here in the States, or if over in the UK, it is Haynes Pro. If you have a subscription to information, this is Shopkeep Pro right here. It directly links with the tool, passes your information through, passes the vehicle information through, passes the code information through as well. So it actually drops me off on a search results page. So I'm going to back up one page here. This is where it would drop you off when you're in here. I was in here earlier. See, I get search results and related results. The related results is once again based on real world data. So if I'm going to go to P0356 and I really think that's an ignition coil problem, I'm going to go in here. This gives us all of our information on the vehicle based on the manufacturer information or our SureTrack real world information as well. So you see it's laid out, no TSBs there. That would show up there. Causes and fixes. Guided component testing is available here as well. But I'm going to come down to my wiring diagrams. Interactive wiring diagrams. All right, so we're taking a look at this vehicle. I know it's a 3.5 liter, so it filters it down by that. I would like to note that engine performance circuit, 3 of 5. So that indicates to me this diagram, if I were to print this out, it's going to take up 5 pages, or we'd call that 5 panels. All right, so 3.5 liter, 3 of 5. Why does it pull me to 3 of 5? If I click on it and open it up, we will see that I have highlighted wires. It drops me on the page where the coil lives, because I'm looking up a coil, and then it highlights the wires on the coil as well. So if I hit this eyeball over here, it will dim the rest of the wires, and I can see there's my coil wire. ECM's up here. I can zoom that in if I want to see it a little bit better, right? I can zoom that in. There's my ECM up there. I went in a little too far. Let me back up a little bit. Right, so there's my ECM right there. If I go down a smidge, got to use that arrow tool. If I go down a smidge, we see that it does go off the screen as well. So all my coils are highlighted. It does go off the screen. So if I go to the right, you're going to see where that goes. It goes through the page. The highlight carries over. And then I'm just going to scroll up and let's find out where that wire goes. Pretty sure I know where it goes, but we're going to look anyways. All right, so that goes to my ignition fuse. All right, 15 amp ignition fuse. Now let's say I'm in here and I want to check powers, I want to check grounds, I want to check the coil. Where's this fuse? So if I go, it says engine room junction box assembly. See how it's highlighted in blue? I click on that blue. It's going to open up a new search box on the left here for me. So now I have very similar information to what I saw on the coil, but now it's based on the fuse and relay boxes. So that's the engine room junction box. If I wanted to find out where that is, I'm going to assume it's in the engine room, but I might not know exactly where it is. So this will help me pinpoint where that is. So engine room junction box right there. And then there's my fuses listed there, all from the OEM. You know, then we have some more connector views there, right? So it gives us all this information. And I really didn't have to leave that wiring diagram. And oh yeah, I really didn't have to leave my tool either, because I'm still sitting in the seat of the car because I'm hooked up over Wi-Fi, and I just have this information available because the tool is integrated directly. All right, so all that information. So now I have my wiring diagram information. Now I know where the fuse is. Maybe we check the fuse. Maybe we'll do a current ramp on the coil. So all I need to do is go back home, back to my scanner. It's going to leave me right where I was. Scroll back up to that guided component test meter. Go to my ignition test, like I said before. And I could do component information. In this case, we have secondary tests listed. So I can go in there. I have a secondary ignition test I could do to get a pattern, or I can do a current ramp test. So I'm going to do the current ramp test. Once again, looks very similar to that BMW we showed earlier, right? So it's going to be a lot of the same information. It's going to say put it on the positive wire. There's what the current ramp is going to look like on this vehicle. If it goes up sharply at the beginning of the ramp, suspect shorted coil windings, right? So you'd see that. Now, this is something I can't simulate, but if I hit view meter, we would see a current ramp going on here. I can't simulate a current ramp with this with the tool without being hooked up to a car, but you would see the current ramp going up here, and like I said, automatically sets the scale, and automatically sets the sweep time for us, and automatically puts this trigger point in for us as well. So all that automatic setup, all of this was based right on that code. Huge time savings I could think versus the way I used to do it. I'll tell you, at the dealership, this is way faster than how we would do it there, and test that coil, right? So let's say we did test the coil and it tested bad, then we would know, we replace it, test it again after you're done to verify that you actually did fix the problem. Not that I'm not saying that you wouldn't fix the problem, but is the component good? And I'll ask you this, you ever gotten a brand new part in a box that didn't work? Right? That's why we always want to test those components as well. Test them before to verify that it is bad, and then test it again at the end to make sure that it is good. And then once that is the case, we're in good shape and we don't have to worry about it anymore, right? We can send it on down the road and move on to the next thing. So a lot of information in there on coil just based on this code alone. I showed you some shop key information on that as well, how the tool might help us in there, where we might access those tests. If you do want more information on the testing coils and such, if you have one of our tools with guided component tests in there, so it'd be a Zeus, a Veris, a Modus, a Vantage, a Triton, any of those tools. If you go into guided component test and you load in the training and classes, there's also built-in training and classes in there for you as well. If we go into how-to, there's some ignition tests in here, different coil current ramping tests in here as well. There's a wealth of classes. There's over 65 different categories of class in here as well. So like 20-minute current ramp classes right there on the bottom if you wanted to learn more about that. All right, so that is my time for this evening. Let's talk about next week. Next week is part 1 of 2. So we will be doing, oops, I didn't change the title on my slide. I need to change that a little bit later. So this week is component testing. Next week is electronic throttle control part 2. Right, so electronic throttle control, it'll be a 2-part course. We're going to go over, starting with the history of throttle control through two-wire throttle position sensors all the way up through the modern with the accelerator pedal sensors and the electric motors and all that run our modern vehicles out there. So it's going to go through both parts. It's going to be a 2-week series. So first week, we're going to go over some history, accelerator pedal position sensors, early throttle control sensors, and then we'll go into the full electronic mode in the second class. So as I said, sorry about that, have an error on the slide there, but it will be electronic throttle control next week. Same time, same place, 6 and 9 Eastern. If you want to join me on Zoom, snapon.com/OT to register, and then you can join me there. Or if the early session goes to YouTube, so make sure if you use YouTube, you follow us, you give us a subscribe there, subscribe to the channel, and then make sure you hit that little notification bell next to the subscription so you're notified every time we go live. I've been seeing a lot of folks coming up and seeing us, hanging out with us on YouTube. So I definitely appreciate that. The community has been growing. So youtube.com/Snap-on Diagnostics is where you'd want to go for that. Also note that we record these live streams. So I do the live streams, I'll do them in a block of 5. All right, so the first time we do a block of 5, they get recorded to YouTube, and they're there for if we ever delete them. The second time through, we will live stream it to YouTube, so you can at least catch it live. But then we set it to private after that, so we don't have duplicates of the recordings. But you do have 4 chances to catch each one of these classes live, because we do it 2 times a week. So previous topics, though, if you want to go check the YouTube channel, intro to ADAS, data bus testing, code-based diagnostic workflow, thermal imager, module setup, a wealth of information there. And this is class number 20. So episode 19 was last week. That was oxygen sensors. This week will be episode 20 on ignition coils. So I definitely appreciate taking your time. Check those out. If you want more information on ignition, we have episode 15, ignition testing for techs, and episode 5 is a ignition system testing overview as well. So definitely check those out. Now it's time to get to the questions. I see comments and questions rolling in fast and furious here. Before I do, real quick though, let me just make sure I talk about my buddy Al. Al helps me out on these classes, and I help Al out on his classes. So what we do is Al, Mondays, Wednesdays, and Thursdays, does scan tool specific training, platform training, we call it. So Mondays is on Apollo, Wednesdays is on Zeus, Thursdays is on Triton D8 and D10. Same time, 5 and 8 Central. If you go to snapon.com/OT to register on Zoom, he does not live stream those. Those are just live in person in Zoom. You can feel free to ask questions and get some kind of more of like a personalized help with your tool if you're interested in that. Goes all the way from let's set up the Wi-Fi through, hey, let's walk through intelligent diagnostics. What does intelligent diagnostics do for us? A very good, thorough dive on that. Let's set up your free Snap-on Cloud account. We do that as well. The Monday class on Apollo is about an hour, going through all that. Wednesday and Thursday, Zeus and Triton, those are closer to 2 hours with a break in the middle. And those also add, over and above the scan tool functions, we go through the guided component test, meter, scope, all of those things on those tools as well. So definitely check that out with Al. Sign up snapon.com/OT to check out Mr. Al. So let's go to questions. I've been seeing quite a few on YouTube there. So let's see. Calgary, let's see. Christian from Norway. Hi. Thank you for joining us from Norway. Wally, I was using a Zeus there. I think I mentioned that a little bit earlier. So thanks for the question there. Joseph Neal, absolutely. First thing, always check that wiring diagram. If you think you're going to test something, check that wiring diagram first and make sure that you know how it's wired up and how it works. Check powers and grounds. K Morris asks, does the Varus have a built-in attenuator? We actually don't need attenuators when we're checking ignition because of how our probes are set up. So it is set up to handle 400 volts, but the probe itself does the conversion or the attenuation that we would need. So we actually don't need a separate attenuator for a Varus or a Zeus or a Modus or a Triton or a Vantage. Any of our tools doesn't need it for secondary ignition there by using the proper adapters. And then let's look over to Zoom. Gino, hi from Ontario. Thank you very much. And Bill, I can use your Duramax if you need a truck for a case study. Very thankful there. Bill, I don't know where you're located, but if you're around me, then that we might be able to take you up on that offer, right? So, or maybe when I'm in the neighborhood, we can help you out, because I know we are planning at some point doing some diesel classes as well. So Duramax would be good to have. Thank you very much there, Bill. All right, with that, I think we covered everybody. I know there's a little bit of a lag on YouTube, but that's okay. I think we got everybody there. So I'd like to take the time to thank everybody for taking a little bit of time out of your busy week to spend with us. Hopefully we got a few more interesting test tips and nuggets on ignition coils this week. And hopefully you'll join us next week, same time, same place. And we will go through electronic throttle control part 1 of 2 next week. So enjoy the rest of your week there. Thank you once again for joining me. Definitely appreciate it. And take care of yourselves out there. Take care.